Welcome back to another one of my applications of differentiation videos where I show you how to apply derivatives to problems. Right now I'm going to be teaching you maximas and minimas, or the extremas, or the extremums, or maxes and mins, or minimums and maximums, whatever you want to say it. Basically the point where it comes up to its high bit and the point where it comes to its low bit. And I'll add a few things in between. But anyway, let's get started. So, if you've watched the other videos, you know the process. We basically have a derivative, or a function, or a derivative, not yet. We have a function, and within a domain, and what we're going to do is derive this function, get critical numbers, use those critical numbers and find critical points, use those critical points to find maximas and minimas using the first derivative test. Okay, so let's get started. The derivative of 2x is just 2, and the derivative of this, well, this is cube root of x is the same as x to the power of 1/3. So that's a 3, by the way. So basically the derivative is 1 on 3 multiplied by x to the power of negative 2 on 3. Which will equal 2, take 1 on 3x to the power of 2 on 3. Okay, now we have our derivative. What we're going to do now is we're going to solve for 0. So we're going to let this equal 0. And so we'll have 2 minus 1 over 3x 2 over 3. Okay. So what we're going to do basically is multiply throughout this whole thing 3x to the power of 2 on 3. Okay. So that will look like, it'll be 0 on this side because whatever you multiply to 0 will be 0. You multiply 3x to the power of 2 on 3 onto 2, and you get 6x to the power of 2 on 3 minus 3x to the power of 2 on 3 on 3x to the power of 2 on 3. So what we're left with is 0 equals 6x2 on 3 to the power of 2 on 3 minus, well, this equals 1. Because it's the same, it's that thing divided by the exact same thing, so it's 1. It's one whole. Add 1 to both sides. That'll cancel out, and that'll have 1 equals 6x to the power of 2 on 3. And we're going to cube both sides. That'll just be 1 cubed is 1. That'll equal, or when you cube something like this, we're going to cube the 6 and then we're going to cube the x 2 over 3. So when you cube the 6, it's going to be 216. And when we cube the x 2 over 3, well, the 3 is going to cancel out this 3 and we're going to be left with x squared. Okay, Now, okay, so we're going to divide both sides by 216. So it's going to cancel out, and that's going to bring it over here as 1 on 216 equals x squared. And square root both sides, we end up with x equals the square root of 1 over 216. Or, which is our other x value, x equals the square root of 1 on 216, but there's a negative in front of it. Because if we squared this, if we squared both sides right now, we would end up with that. That's why it's a plus or a negative. Because if we square, if the negative's not on the inside, so it's not a problem. If we've still got a positive number within the square root. But if we squared this whole thing right now, including the negative, we squared that whole thing, we would get this. That's why when you reverse it, you have both. Okay? Okay, so these are our critical numbers for that point. Now, the function, or the derivative, is, just to refresh, 2 minus 1 on 3x to the power of 2 on 3. Now what we're going to do is we're going to set the derivative equal to, does not exist or undefined. Basically we'll be focusing on just the bottom part. So 0 equals 3x 2 on 3. Rearrange that, multiply, divide, whatever. We end up getting x equals 0. So this is our other critical number. Now what we're going to do is we're going to sub this number and these two numbers and the domain, which is -1 to 1, into our critical points test. So our critical points test, we basically have x, let's get the x value, the critical points, and we sub them back into the function, original function. And if they spit out a number, which this one spits out somewhere, I'll use the approximate, somewhere around -0.27. That's tick because it spit out a number, therefore it's within the domain. If it comes up with an error on your calculator, then it's not within the domain. We'll put x, oh, my bad, I'm looking at my notes wrong. If we put sub in 0, we get exactly 0. If we sub in, yeah, just remember that's my mistake. If we sub in x to the original function, we get, if we sub in 0, we get 0. Anyway, so x, when x equals the square root of 1 over 216, then the function, if we sub that in, then the function equals around about -0.27. That's it. And that's a tick. That means it's within. So these both so far are within the domain, so they're both critical points as well as critical numbers. Now what we're going to do is we're going to have x equals the negative square root of 1 on 216. We sub that back into the function. That spits out positive, or approximately positive 0.27. Okay, now x equals -1, because that's the domain on the negative side, on the far left, basically. We sub that in, and we get the derivative equals the derivative equals, I think that's -1. Yeah. Let's just double check that. So we have 2 multiplied by -1 minus cube root of -1. That spits out -1, yeah. And x equals 1. Well, that spits out a 1. So therefore, tick, 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 all of these are critical points. Now, I'm going to do the first derivative test now. And when I go to do the first derivative test, I'm not going to put the domain in, so I'm not going to put the -1 or the +1 in, because those are the endpoints. There's no point putting in those endpoints just for this test. So we have our x values, derivative, and what it's going to look like. I'm not going to draw like shape or anything there, but okay, so we're going to have a gap between each of our critical points except the domain ones. So here we have negative root 1 on 216. We leave a gap. Here we have 0. Here we have a gap again, and then we have positive square root of 1 on 216. And then we have a little bit on the end, so we have a gap in between and on either side of our critical points. So let's pick a number between this and negative 1. So I'm just going to pick negative 0.9. And over this side, I'm just going to pick positive 0.9. Between this number and 0, I'm going to pick negative 0.05. And on this side, I'm going to pick 0.05 positive. Okay. Now, these values, these will equal 0 because this will equal 0 when you sub it into the derivative, and this will equal 0. Funny enough, when you sub this into this, it comes out with a math error, and I'll explain that in just a bit, but for now that just equals NA. So if you did that and you get a problem, don't stress. And over here, if we sub this negative 0.9 into the derivative, we get a positive. If we sub this negative 0.05 into it, we get a negative. Over here, if we sub this positive 0.05 into the derivative, we get a negative as well. And if we get a 0.9, if we sub 0.9 into the derivative, we then get a positive number. That means it will come up here, it will flatten out here, it will go down here, it will go down here, it will flatten out here, and it will come up here. So we can therefore say right here is a maximum because it goes up and it flattens out and it goes down, so therefore it rounds off at the top, therefore that's the maximum point. And here it goes down, therefore the part where it's at its bottom is its minimum, so therefore this is a minimum and this is a maximum. And here, well, I usually just put a dot because whenever I get NA, it usually means that it's like an endpoint or it's just a dot, because in this situation, the fact that the normal function, if we sub this x value in, we get 0. But if we sub that in there, we get 0. And if we then derive it and sub it into there, we get a doesn't equal 0. It's undefined. Okay? So that means that it's a point of inflection, from what I was taught anyway. It means it's a point of inflection, which means this will be a saddle shape. Okay, so that's the point where it's comes down like that. So it's a maximum and a minimum at the same time, sort of thing. It comes down and it looks like it's going to be a minimum, and then it switches to what it looks like to be a maximum on the other side. That makes sense. Hopefully that makes sense. So the graph will look something like that. Okay? Anyway, so let's draw this graph. Well, first I'd like to say that the minimums, where are the minimums located at? Okay, so the minimum is a minimum over here. Okay, so that's where x equals positive 1 over 216, square root of 1 over 216. And what's the function value for that? That's negative 0.27. Or roughly around there. And also the end of the domain, because this comes up, so that must mean it's a minimum down here because it comes up to this, so therefore it must go down to where the -1 lies. Therefore, at x equals -1, fx equals -1. And our maximums are located at, well, we have a maximum here at -1 on 216, and that'll be a positive. And the other maximum is located at 1 and 1, because it's up here where x equals 1 and it's coming up to that point, therefore that's a maximum. Anyway, now we have these values. Let's draw the graph. So we have fx and now x. Okay, so we're going to put 0.5 here, 1, -0.5, and -1. And we're going to have here -0.5, -1, and here 0.5, and here 1. Okay, so at roughly that point there, minimum is located at, I can't remember what that value is, but it's somewhere around here, and this maximum is located somewhere in the opposite direction around here. Okay, and then we got the minimums at 1, 1, or the maximum at 1, 1, and the minimum at -1, -1. And we have like a saddle shape here. So therefore, if we draw it, it'll come up, it'll come down here, it'll go at saddle, and then it will come up like this. And we draw circles here to indicate that these are our endpoints. A saddle doesn't really look like that. It's sort of weird how it works, but Google it if you want to. But we won't really be worrying about saddle points because we're looking for minimums and maximums. So here is our absolute minimum. Here is our absolute maximum. Because this is the highest point, like in the vertical direction. This is the highest point, therefore it's the absolute maximum. It's the absolute highest point. And here is absolute minimum because it's the absolute lowest point. And this here is a minimum, is a maximum, but it's a local max. And here is a there and there is a local. That point there is a local min, because it's still got, if you go to the right it's going up, and if you go to the left it's going up, therefore it comes down to a minimum, but it's not the lowest point, therefore it's a local minimum. It's a minimum to its surroundings, and here is a maximum to its surroundings, but these two are the absolutes for the maximum, and it's the highest point, and this is the lowest point over here. Anyway, I hope you learned something from this video. Thanks for watching, and I hope you have a good day.